We're going to take a look at the homework that we had last night. There was 2 bits of it, worksheet number 24, which you guys did well on, and worksheet number 25, questions 2, 7, 11. I want to real quickly go over question number 7 here, which says, find the ratio of current activity to the original activity in carbon-14. Now, your version of this worksheet had the half-life of carbon-14 on it. It said the half-life is 5,730 years. The time is 11,460 years. Therefore, the number of half-lives would be T over T1 half ends up being equal to 2. That's not what we're looking for, though, the number of half-lives. That's important. Okay, we're going to need that number, but that's not what we're looking for as a final answer. What we're looking for is a ratio. You guys know what to do when you're looking for a ratio, right? What's the word? What's the D word that you're looking for, that you're trying to come to mind every single time when you're looking for a ratio, Cole? Divide. So if we're looking for a ratio of n to n0, let's divide n by n0. Perfect, right? Perfect if you have the value of n and n0. This is easy. Just divide the two numbers, and the value of little n was irrelevant. But you know what? I don't know the value of n and n0, not at all. So here's what I want to do. I want to take my base equation, n is equal to n sub 0, 1 half to the little n, and I want to rearrange it to solve for n over n0. The ratio of n over n0 is not only equal to whatever number n and whatever number n0 is, but it's also equal to 1 half to the little n. So what I'm going to do here is, instead of dividing these two numbers, I'm going to say 1 half to the 2. When I do that, I get 0.25. So my ratio, I could say, is 0.25 to 1. Right? Or I could say, well, if I do that as a fraction, it becomes 1 over 4, right? I could also say the ratio is 1 to 4. If you were to see this on a test, my guess is this is the way you'd see it written. But if you solve for this, 0.25 to 1, then you could probably make that transition, right? From 0.25 to 1 to 1 to 4. Good? No other issues with that? Okay, one more little thing that I want to do with half-life and radioactivity, and then I want to move on to a new type of transmutation equation. In fact, 2 of them, 2 more types of transmutation reactions called fission and fusion. Take a look at this graph, a radioactive decay curve. A radioactive decay curve is a little bit different than the other graphs that we'll see. The other graphs that we'll see will be straight line graphs. This won't. This will never be a straight line graph for you. It's always going to be n on the y-axis. Okay, that n could be mass, it could be a number, it could be a percent. It's just an amount, the amount that remains after a certain amount of time. And on the x-axis, it's going to be time. Occasionally, you might see the number of half-lives, but usually it's going to be time on the x-axis. Anyway, you look at it, the shape of that graph is always going to be like this. Now, the bad news is, it's kind of an ugly shape if you want to analyze it mathematically. You have to end up straightening it using a logarithmic curve straightening technique, which is, you don't want to go there. The good news is, you won't have to do anything mathematical with it other than read things right off the graph itself. The only things that you're going to have to find from this graph are an amount, an n, or a time. If you want to find an n, then you're going to go up and over and read off the y-intercept, okay? Or read off the value of the y-axis that corresponds to whatever value of x you have. Okay, up and over. If you want to find a value of t, you're going to do the exact opposite. You're going to go over and down. So for instance, probably the most common question that's asked for in one of these graphs is the half-life. What's the half-life of this? Well, how much do we have left after 1 half-life? 50%. If the original amount was 100, then we're down to 50 after 1 half-life. If the original amount was 300, then we're down to 150 after 1 half-life. If the original amount was 17,000, then we're down to 8,500 after 1 half-life. Go to half of what you started with, go over and down, and you read off that value. That looks to be about 2 years. Now, on a test, you're going to be given a lot more grid lines, X grid lines, Y grid lines, so it's going to be a lot easier to tell exactly what that number is. Okay, but you get the idea here. Okay, the idea is the same, okay, whether we can get an exact value or not. How much remains, how How long does it take to go down to 20 grams? Well, let's go to 20 and go over and down. Looks to be about almost 5 years. So it takes 4 point whatever years to go down to 20 grams. What about how long does it take to get down to 80 grams? Well, let's go over and down. Looks to be about a year. Okay, you want to find a time, you're going to go over and down every time. Now, on the other hand, if you want to find an amount, you're going to do the exact opposite and go up and over. So let's say, erase that and say, how much remains after 5 years? Well, let's go 5 years, go up and over. Looks like about maybe 15 grams. How much remains after 10 years? Up and over. Looks to be about maybe 5 grams. You want to find a time, go over and down. You want to find an amount, let's go up and over. Good? The focus of today's lesson is going to be on 2 more types of transmutation reactions, where one nucleus changes into something else. We've talked about radioactivity already, specifically alpha decay, beta decay, and gamma decay. Today we're going to talk about nuclear fission and nuclear fusion. Spend a little bit more time on nuclear fission because it's the one that we see more often. It's the one that has more practical relevance to us, at least right now, more practical relevance to us. Nuclear fission is that process whereby one heavy nucleus splits up into lighter nuclei. This is an example that you see on the board right now of nuclear fission. There's lots of examples that you could see. In fact, there's lots of examples that look an awful lot like this one, but just not exactly the same. You can see in this case that we have uranium-235 that's splitting up into krypton-92 and barium-141. There's also some neutrons there. Those are important, but they're not important in determining what kind of reaction it is. We look at the other things. When we look at the other things, you can clearly see something heavy, 235 protons and neutrons, splits into 2 lighter nuclei. Now, what's the deal with these neutrons? I said they're important. The first neutron is really important because this uranium-235, although it will split up, it will decay on its own eventually, it's going to take an awful long time for it to happen on its own. So what we do is kind of prompt it to happen. We give it a kickstart to happening. It's kind of like, you know, you got an iceberg in the North Atlantic, and it's just ready to break apart. It's ready to split apart. You hear the ice cracking, but it's not breaking apart. So what do we do in order to make it happen? We kind of kickstart it, right? We hit it with a big ship. We run into it with a big ship, and what happens? The iceberg breaks apart. Okay, that's what's happening here. You get this nucleus that's kind of ready to break apart, this uranium-235, but it's not doing it on its own right now. So we kind of kickstart it. We hit it with a big ship, or we hit it with a hammer, which is a neutron, which temporarily actually makes this uranium-236. This reaction actually reads 1 neutron plus uranium-235 goes to uranium-236, which in turn splits up into krypton-92 and barium-141. So for a brief time, it actually becomes uranium-236, splitting into these 2 things, and then 3 extra neutrons. Why are the 3 neutrons on the left and the right side important? Okay, we know why this is important. It's the ship that breaks the iceberg apart, right? We need to get it kick-started. Okay, the catalyst, kind of. Why are these 3 neutrons important? Well, because we don't want to keep firing neutrons at this uranium-235. If we want uranium-235 to undergo what we call a chain reaction, which is a self-sustaining reaction, then we got to have some way of making it happen on its own after we've kick-started it, after we've got it going. So we fire a neutron at uranium-235, gets absorbed, it becomes uranium-236, splits apart into krypton and barium. 3 extra neutrons cause 3 more reactions. We don't need to fire another neutron at uranium-235 because we got 3 neutrons automatically being fired at more uranium-235. That produces 3 more reactions, which produces 9 neutrons. And then those 9 neutrons cause 9 more reactions, which produces 27 neutrons. And then those 27 neutrons produce 27 reactions, which produces 81 neutrons. And then 243, and then 700 and whatever 243 times 3 is. This actually grows, this reaction grows exponentially in a matter of a fraction of a second, so that you get this, what we call a chain reaction, this self-sustaining reaction, where the products of the reaction cause, man, I can't spell when I'm talking, hey? Where the products of one reaction cause more reactions to take place. We also get some energy release there, by the way. About 200 mega electron volts of energy release in each of these reactions. So first one, 200 mega electron volts. And then in the next generation, it's 600 mega electron volts. And in the next generation, it's 1800 mega electron volts, and so on. Within a tiny fraction of a second, you go from 200 mega electron volts to a lot more than 200 mega electron volts. It grows exponentially. This energy, by the way, is enough energy to move maybe a speck of dust. But as this grows exponentially within a tiny fraction of a second, you end up growing the number of 200 mega electron volts bursts of energy that's released, and you end up moving a whole lot of specks of dust. You can do a couple of things with that. You can generate electricity, which can power a city, or you can build a bomb with that and blow up a city, as was done in Hiroshima in 1945 and Nagasaki in 1945. This was the bomb that was dropped on Hiroshima in 1945. It was actually this reaction, this uranium-235 reaction. Okay, it kick-started it by firing something at it. Okay, gets it going. The neutrons cause more reactions, becomes a self-sustaining chain reaction, blows up a city. Do you know that in 1945, when they dropped this thing on Hiroshima, they hoped it would work. They never tested this, not once. Not one single time was this bomb actually tested. You know why it wasn't tested? Because most of the uranium that occurs in nature is not uranium-235. Most of the uranium that occurs in nature is another isotope of uranium. There's only a tiny fraction of a percent of it that's actually uranium-235. So what they needed to do was separate the uranium-235, the fissionable material that they needed. They needed to separate it from the other naturally occurring uranium. It's easy to find uranium, but there's not very much uranium-235 in uranium. They need to enrich it. You ever heard of that term, uranium enrichment? North Korea, Iran, uranium enrichment programs. You ever heard of that? The Americans are worried about North Korea and Iran having uranium enrichment programs, because if they can enrich uranium, then they can build a bomb, right? Then they can build an atomic bomb. Here's the thing, though. It took the Americans something like 3 years to enrich enough uranium to build a single bomb. They used 64 kilograms of uranium in this bomb. That's it, 64 kilograms. And it took them 3 years-ish to get 64 kilograms. Imagine if they had tested this, dropped it, and then said, oh, now what are we going to do? Take another 3 years to get enough fuel to build another bomb? That's why it was never tested. Do you know that when it was dropped? 64 kilograms of uranium that was dropped on Hiroshima, less than 1 kilogram actually underwent nuclear fission. Less than 1 kilogram actually exploded. Less than 1 kilogram of uranium was enough to blow up that city. Why do you think the other 63 kilograms didn't explode? Any takers on that? The problem with the design of this is that it has to be in such close proximity, because these neutrons have to join with this uranium. This reaction takes place so quickly that the bomb literally, within a second, blows itself apart. so that it's spread apart so much that these uranium can no longer fuse with this, with these neutrons can no longer fuse with this uranium. So it literally blew itself apart before the other 63 kilograms could actually undergo nuclear fission. They got the results they wanted, though. This one is called Fat Man. That one was the one that was dropped on Nagasaki. What was it, a week later? A few days later? Don't remember the exact timing of it. This was tested. In fact, this was the only nuclear test ever done prior to the bombs being dropped in Japan in 1945. They actually dropped one of these in New Mexico, in the desert in the United States, to test it. What does it do to sand when you generate a whole lot of heat? I mean, this would be an unbelievable amount of heat, right? What did it do to sand? Turns it to glass. I mean, there's people that were working on this project that went around, hey, this is cool. There's glass in the desert caused by this nuclear bomb. Let me take some of this home as a souvenir. People that did that because they didn't know any better. The problem with that is that the products of nuclear fission are highly radioactive. Highly radioactive. I don't know how many, probably thousands of Americans ended up dying as a result of this bomb, as well as Japanese, because of the fallout from the nuclear test that was done in the desert in the United States. So this chain reaction is a self-sustaining reaction that's these neutrons cause more reactions. In the uranium-235 bomb, which was the little boy that was dropped in Hiroshima, or this is actually plutonium-239, or the plutonium, not uranium, plutonium. So these neutrons fuse with more uranium in the case of this one, or they fuse with more plutonium in the case of this one to cause more bursts of 200 mega electron volts. This exponential number of them becomes self-sustaining because these neutrons keep sustaining it. Mass defect, one more term before we go to fusion here. Mass defect is the missing mass. Let me put that in quotation marks. The missing mass. When this reaction takes place, when any of these nuclear reactions take place, we always lose a little bit of mass in the process. Now, in chemistry, you would have learned that that's not possible. Mass stays the same. The law of conservation of mass says that the total amount of mass will always remain the same, but it doesn't. That's not quite true. In a chemical reaction, it does, but not in a nuclear reaction. In a nuclear reaction, you lose mass, but it's not destroyed. It's just changed into something else. What's mass changed into? Ice can be turned into water. Mass can be turned into energy. The missing mass gets converted to this energy, and it's this energy that ends up getting released. So, chain reaction is this self-sustaining reaction where the neutrons cause more reactions. The mass defect is the mass that disappears in the reaction and gets converted to energy. The other type of reaction that I want to talk about today is called a nuclear fusion reaction. It's the exact opposite process. If fission was where one heavy nucleus splits apart into lighter nuclei, then fusion is when two lighter nuclei fuse together to form one heavier. You can see in the fission reaction, if we ignore the neutrons, clearly one heavy thing becomes two lighter things. If in the fusion reaction, we ignore the neutron again, two lighter things become one heavier thing. This is what we call, H2 is what we call heavy hydrogen, deuterium. Normal hydrogen has one proton and no neutrons. It's H1. This isotope of hydrogen is twice as heavy, and it has one proton and one neutron. When you can take these two hydrogen nuclei and bring them close enough to actually fuse together, they actually become helium-3. In that process, they eject another neutron, which for us isn't really relevant in fusion, but they also release a lot of energy because of the mass defect. You lose mass in the process that ends up being converted to energy. But there's a problem with this. There's a problem with making this happen. The problem is that hydrogen and hydrogen are both positively charged. The nuclei are positively charged. You want to get them close together so they fuse together. But the closer you bring them together, the bigger the force of repulsion is going to be. Right? As R becomes smaller, then F becomes bigger, bigger, bigger. It becomes unbelievably big, this force of repulsion. So they don't want to fuse together. They don't want to come together. We have to overcome that force of repulsion somehow, and we do. We overcome that force of repulsion by supplying energy to it on the left-hand side, usually in the form of heat. So you pump a bunch of energy into this. You energize these hydrogen nuclei so that they can overcome that repulsive force, fuse together, release a neutron, and release even more energy on this side. Now, we have a chain reaction happening here as well, just like we did with the fission reaction, but it's not a result of the neutrons as products. It's not the result of the neutrons forming more reactions with the uranium or plutonium like it does on this one. Rather, it's a result of the energy. Some of the energy that's produced in this fusion reaction goes into causing more hydrogen nuclei to fuse together. So again, it becomes self-sustaining because you get more energy out of it than has to go into it. But it's self-sustaining for a different reason. It's not because of the neutron products, it's because of the energy products. Where's the most common place you would see a reaction like this taking place? You see it every day. Good, Ryan, it's the sun. Now, the reaction that takes place in the sun isn't exactly this fusion reaction, but it's like this. Hydrogen fuses with hydrogen, produces a lot of energy. Hey, you look up at the sun, what do you see? It's bright, right? Why is it bright? Because it's a massive nuclear bomb going off continuously for billions of years. How does it sustain itself? Well, you know what? The sun's hot. The sun's really hot. So some of the energy that's produced by the sun goes into causing more hydrogen to fuse together, which produces even more energy, which causes more hydrogen to fuse together, which produces even more energy, and so on and so on and so on. This can be used to build bombs, but it can also be used to build power plants. We have lots of nuclear power plants in Canada, particularly in Ontario, using this technology, not this reaction per se, but this technology of nuclear fission. Okay, the benefit of this is it generates a lot of energy. Now, it doesn't generate electricity. It generates a lot of heat. But that heat can be used to boil water, which creates steam, which rises and turns a turbine, right, moves a magnet through a wire, generates electricity. It produces a lot of electricity. The downside to it is that these products are highly radioactive. So the material that comes out of the nuclear reactor, although it's not released up into the sky as greenhouse gases, it's not good. It's more containable than greenhouse gases. We can keep it together. So in that sense, it's better. But highly radioactive is very, very dangerous. So what do we do with it? We usually end up burying it and then encrusting it in concrete so that these particles that are released from these nuclear reactions don't ever see the light of day. We can build bombs with this too. In fact, post 1952, that's what the Americans used, is fusion bombs. This was the fusion bomb, the H bomb that the Americans built in 1952, which is, by the way, way more powerful than anything they ever dropped in Japan. This released about 20 kilotons of energy in Japan. That's measured, by the way. I always measure the strength of a nuclear reaction in terms of how many tons of TNT exploding equivalent it is. So 20 kilotons, a 20 kiloton bomb would be the equivalent of dropping 20,000 tons of TNT on Japan. I mean, that's pretty massive, right? 20,000 tons of TNT on one city. But fusion bombs especially the bombs we have now, are way more powerful. They're in the range of megatons, not thousands of tons of TNT, but millions of tons of TNT. They're almost infinitely bigger than the bombs that were dropped in Japan in 1945. So we can use these to build bombs as we can these. But we can't use this to build power plants like we can fission. Fission we can control. We can control this, right? Hey, you don't want it to become an uncontrolled chain reaction? Well, let's absorb some of these neutrons. If we don't have 3 of these neutrons causing 3 reactions, and then those 3 reactions causing 9 neutrons and 9 more reactions and so on, if we don't want it to progress that quickly, then we just take away some of those neutrons. We absorb some of those neutrons. We can't control this fusion thing. We can't control it. So basically right now, if we build ourselves a nuclear fusion reactor, we're basically building ourselves a bomb. You're not going to power a city. You're going to blow up a city. I do think that sometime in your lifetime, this will be reality for power. I do. You're 17, 18 years old, and I think at some point before you guys die, I think that we will see nuclear power plants built on fusion technology. We will learn how to contain it. We'll learn how to control it so that we can use it to generate power. If we can do that, I mean, it's a game changer. It generates a lot more electricity than anything we know of. Generates a lot more electricity than wind power and solar power are clean, right? This generates way, way more power than that. Generates way more power than coal, which is filthy. Generates way more power than fission even, which is clean in a sense, but dirty in the sense that it's got this radioactive products. The real benefit of it comes from not only the amount of electricity they can generate, but also the fact that the products here are safe. These aren't radioactive. So here, you're generating a lot of electricity, but you got this nasty radioactive materials that are left over as a result, this waste that you got to deal with. Here, you got lots of electricity, you got no greenhouse gases, you got nothing poisonous being released in the atmosphere, and you got no radioactive material left over. It's perfect, right? Except that we don't know how to control it yet. Two reactions up on the board right now. One of them's fission, one of them's fusion. Which one's which? Parker? Top one is fusion. How do you know that? I'm sorry? Okay, be careful with that. Okay, that works here because in the end, if you got something so light on the left-hand side, it's not going to split up, right? It's going to fuse together. But it's not necessarily hydrogen. So we're not looking for those particular elements, although that was the example that I gave you. It could be some other elements that are fusing together as long as it's really, really light, right? Bottom line is we got two light things on this side. We got one, not heavy, but heavier thing on the right side. The neutron, yeah. Okay, that's there, but we're not paying attention to that in terms of quantifying it as an extra thing. It's not two things going to two things. It's two things fusing together to form one. Therefore, if that one's fusion, this one's got to be fission. And we know that by process of elimination, but also because uranium-235, one heavy thing splits apart into two lighter things. You can see a neutron over here. You see three neutrons over here. Hey, by the way, it's not always three neutrons over here. Could be two, could be four. Depends upon the exact reaction, Quinn, that's taken place. And this one, it's three. Okay, we got to balance everything out, right? 236 and 92. 36 plus 56 plus 0 is 92. 92 plus 141 plus 3 neutrons gives me 236. That's why we need 3 neutrons on the right side of this one. Depends on the reaction. Maybe we only need 2. Maybe we need 4. But there's always going to be neutrons on the right side. They don't play any part in determining what kind of reaction it is. Okay? But they do play a really important part in sustaining that. What's the word I'm looking for? These guys are the things that sustain the two words. the chain reaction.